Good afternoon, everyone. It's such a great honor to have Dr. Doug Lanman to be the colloquium speaker today. And Doug is the Senior Director of the Display System Research at Meta's Reality Lab Research. And Doug has been leading research in a wide range of imaging and display technologies, which he will tell us today. And Doug is also an affiliate instructor at the computer science department at the University of Washington, where he teaches how to build VR headsets from scratch. And Doug received his bachelor degree in applied physics with honor from Caltech in 2002, and his master and PhD degree in electrical engineering from Brown University in 2006 and 2010. Prior to Meta, he was a senior research scientist at NVIDIA research labs and also a postdoc research associate at MIT from 2010 to 2012. And without further ado, let me pass the podium to Doug, and he's going to give us the talk. Doug?
Hi, can everyone hear me, hopefully?
Yes, it's yours now.
Great, thank you so much for the introduction, Hong. Really wonderful to present to students and faculty and staff at Arizona. Of course, it's no secret Arizona is a feeder school around here at Reality Labs Research at Meta, right? One of the leading optical science schools in the world. So very proud to present to you. You know, even though my background is in computer science and applied physics, I've picked up a little optical science over the years. But of course, this talk is about how optical science combines with every other discipline: human vision science, computer science, graphics vision, AI, and comes together into a system that is generally useful, we hope, for everyone on this planet. So I'll dive into that challenge. And generally, the audience for this sort of talk are graduate students. That's generally who I'm speaking to. And at one point in my career, I was an undergrad or grad student sitting in an audience like this. And I heard some talks that inspired me. I heard Paul Debevec come and visit my little class on computer vision at Caltech, and that inspired me to enter this field. And so it's, of course, I'm always looking for the one or two people in the audience that are maybe on the fence. You know, AR and VR has been around for a while. You know, where is it on the curve? Where is it in the hype cycle? Well, I hope, if nothing else, those of you who are on the fence may see that there's quite a lot of room for innovation in this field. And if, like me, you're inspired to cross disciplines, I really can't think of a broader set of challenges. That's why I work on this more than anything else. It's because it's the most interdisciplinary engineering challenge I could associate myself with. So that's my premise. I'm going to dive in. I have some new stuff to share. I have some stuff that if you've seen me present before, you might have seen before. But I'll try to keep this interesting. And of course, I want to get done fast enough that we can get to questions, which is always the fun part. So what's the question we want to start with? Well, it's become the question of my team, myself as a researcher. You know, what is the ultimate display, right? So even if this isn't what you think about every day, you can tune me out and just sort of have a thought experiment while you're in this meeting. Think about, what is the answer, right? You've lived your whole life, all of us, no matter how old we are, surrounded by displays, televisions and laptops and cell phones and smartwatches and cinema screens and everything else. But where is it all going? Where is it going in 10 years? Where is it going in 100 or more years? Well, you should do the literature search. Brilliant people came before us. One of them is named Ivan Sutherland. And in many ways, he gave birth, at least in the academic community, to modern AR, VR, head-mounted displays and wearables. It was just one stop on a very storied career. But in 1965, he wrote a 2-page memo. It takes you less than 10 minutes to read. I encourage, just go read it. It's worthwhile reading. But, you know, this is a good chunk of the memo right here, this paragraph. But he tried to answer this question, not for 1966 or 1967, but for all time, what would the ultimate display be? And of course, he concludes it's not a 2D flat screen. The ultimate display would, of course, be a room, right? Not just a room where we control the photons, but matter itself. And so for those of you who grew up with sci-fi, of course, you know this became the idea of the holodeck. And we're nowhere close to controlling matter in a macroscopic scale and assembling atoms as he describes. We're still playing around with photons, but the spirit of this, I agree with. This is where we're headed, and this is why there's plenty of room left in this field. And this is what he did. My understanding is, he gets a lot of credit for creating this headset, but I think it was actually developed by Bell Helicopter. I could be wrong. Wikipedia could be wrong. But he got a hold of this headset, and what he did is he created the first real demonstration of spatial augmented reality. And so here it is. It's often mistakenly called the Sword of Damocles. That's not the name of the headset. That's the name of this big pole that's holding the tracking system. It's a set of rotary encoders. So here we are in the mid-1960s at Harvard with a rack of computers that is a lot like our modern GPU fixed function pipeline, rendering wireframe cubes stabilized in the world. And so this was his attempt to imagine now, how would some fraction of this room be created in the 1960s, the 1970s? If we run this forward, back to when I was in elementary school or starting to get into college, this room started to literally exist. We ended up with VR caves. NSF funded multi-site centers of excellence to explore VR caves, and you might find them at all these wonderful universities. I used to work on this sort of thing. The first VR demo I ever saw was a single wall of a cave at Caltech, and it really inspired me. That and the lecture from Paul Lebevic, I'm like, yeah, why am I doing applied physics? This is a system I could really work on. But to me, the idea of this cave is so wonderful, right? That it's not just an immersive environment. It's anything you can imagine. Any story ever could be depicted on this device. But the question is, do we really need a room? And so when I step back, I think we can generalize Ivan's challenge even more and not worry so much about the room versus the flat screen versus the whatever. There's this challenge that I think within the century, we will pass what I call the visual Turing test, right? So whatever your display is, imagine it's just a boring old laptop screen. Could we get it to a point that the photons emerging from it are perceptually indistinguishable from a hole punched through your laptop? And so that everything, focus cues, specularity, parallax between your two eyes, everything is faithfully reproduced. And even though there's sampling, even though there's compression and digitization, that reproduction on your retina is good enough the human visual system believes it's real. That's the goal. I'd start small. Can you even make a smartwatch screen that is a hole into another reality? No, definitely you cannot at the moment. I think this is the challenge I've set myself and my team and my colleagues in academia and industry on. Can we really pass the visual Turing test? Can we take things that are gimmicks now, like stereoscopic glasses, shutter glasses, polarized glasses, caves, rudimentary AR and VR systems? Is it lunacy to believe we could actually carry this far enough? And so once you start imagining this, now you do the literature search, right? So if I was applying for a faculty job, there's my research statement. That's what I want to solve. But where are we at in the arc of history? Well, now I put on the industry hat and I sit back and say, you know what? Our life is very, very, very crowded with devices already, right? Those who came before us filled every niche, every moment of our day. There's a screen built for the purpose, right? From giant cinema screens through laptops, tablets, phones, watches, you name it, there's something. And when I look at this, I realize there's a trend happening. If you go to the left here, to the right, things are becoming much more portable over my life. So the screens are getting smaller, but we can take them anywhere we want. They're very personal, right? It's not meant for 3 people to look at a smartwatch screen, just one person. But that's come at a huge cost when you think about the visual Turing test. Our displays are getting less immersive, right? That 19-inch CRT monitor I had in the early 90s would be more immersive than my 13-inch laptop screen is today in many ways. And so when we go in the direction of immersion, we start to see things get really impractical, right? If you put on shutter glasses in a cinema, big screen, immersive, go into a cave, even more immersive. And then finally you get to virtual reality. And so this way of looking at it is one of the reasons I chose to work on VR. Is something very strange happens on the left side here. In a sense, you go around the swing set and you have the most immersive device, potentially the full human field of view, 6 degrees of freedom tracking, but it's entirely portable and it's entirely personal. Every photon can be customized to just a single retina. That is a unique thing that a cinema or a cave cannot do. And I think this is where, realistically, as as a researcher, I believe we will pass the visual Turing test first, right? I don't think flat screens or other techniques, other displays have a good chance, because the closer you get to passing the Turing test, the more you feel the constraint of a small canvas, a small rectangle floating in front of you. So that's why VR. Then we look at the spectrum and we say, okay, maybe not today, maybe not tomorrow, but AR offers everything we want, right? And Professor Hua obviously began this field, has contributed so much. There's so many things we could talk about in AR. Today, a lot of my talk will be about VR because there's so much happening. But I do believe, right, AR really is that destination where we could pass the Turing test anywhere in the world with a portable device and really get the limit of what a display surface that's non-invasive to the human brain could achieve. Okay, so there you go. That's the setup. Now, for the researchers out there, what are the real challenges, right? There's plenty of publications, but are they actually working on the core challenges, or are they just interesting sort of footnotes? Well, I'd say this is what I learned for the students out there is the first decade of my career. When I was an undergrad, a grad student, a postdoc, I did a lot of this stuff, right? SIGGRAPH papers with weird layered displays and shining lights to reconstruct 3D models. And I'm very proud of that work, but it felt like a random walk. I was just grabbing low-hanging fruit, trying things with my friends. It wasn't pointed towards something. And so I think as I've gotten further into my career, as I've built a team, I realized, life is short, time is short, focus matters a lot. So if you ever end up in a situation like me, I think it's worth pausing and not looking at what's being accepted in the academic community, but the real problems that need to be solved if you want to do something like pass a Turing test. So it's very easy to do this. It only takes an afternoon. Just look at the state of the art. Here we are. This is Quest 3. These are my personal opinions, but I think there's a lot I can beat up on, even though I work at this company. First of all, it weighs half kilogram, right? That right from the get-go means we need to work a lot on form factor to get this down to glasses, which is what I believe we need so that people can be comfortable all day wearing these. And the thickness, right? If we want to be socially comfortable, I'm not sure I want a 7-centimeter device. Also, just the cantilever in front of my face of all that weight is an issue. So for me, personally, personal opinion, comfort is vitally important. We all know that, but I'm not seeing a huge progress in the field on this vector. So form factor, solving vergence accommodation conflict, correcting every last optical, geometric, and perceptual distortion, solving for prescription vision in an elegant way, solving for faultless pass-through. These are table stakes, and only some of these things will you actually see active academic work on. Now, if you ignore the weight of the headset, the ergonomics, and you put your head into one of these things, whether it's AR or VR, you'll see in terms of the visual quality, the realism, the Turing test, there's just some base things we need to tackle, right? Resolution of every device you own is retinal, except for AR and VR headsets, right? It's 1 ArcMet 2020 resolution, acuity, except for AR and VR. We have to solve that. The value of AR and VR is in field of view. It's what's different than every other display. We got to push that to the human visual limit, but in an elegant, interesting form factor. Since it's a personal device, we can finally get the full dynamic range needed to depict at least indoor environments. Can't do that. The brightest HDR TV is far from the brightness of a natural scene. Color gamut, occlusion, pass-through, all these things are core. And so this is, again, like as a researcher, not all of these topics are popular in Optics Express, in Optics Letters, whatever it is. But I think this is the real area as a field we need to push with intention over years. And if we can do that, what's it all leading to? Well, one thing would be you created a portal so that anywhere on Earth you can be with anyone with the fidelity, at least visually. We'll let someone else worry about the other senses, as if you're truly present. And I think for all of us, that's transformative, right? Most of these students probably aren't from Arizona in this lecture, right? I'm not from Seattle. I have friends, family across this entire world. I have interests that go beyond the distance I can easily drive in a day. Perhaps we can close that gap. It's not teleportation, but it's perhaps the closest we get this century. All right, so now that's my premise. That's the job statement. Now let's just do as much as we can in the time we have on the technical details, right? And so this is a retrospective of about 9 years of research from myself and my little team at Reality Labs, trying to go with intention towards this direction. So there's no specific order here, and I can't get through all these topics, but my team has methodically tackled this space of passing the Turing test. We have dozens of prototypes we've built. It's probably the thing our team's most well known for in industry. I'll show you some of those prototypes. I'll show you some new ones we haven't shown before, if time allows. But let's just start going through this. So imagine you end up, you get your dream as a graduate student and you get a job as a faculty or a research team lead early in your career. Well, now, you got the funding, you have the time. Now it's just your direction. You have to choose which way to go. You could always debate this, but when I think about AR and VR, I came to form factor as the first and most important thing my team needed to tackle, and myself. Everyone can debate whether something other than glasses would be acceptable, but we know glasses are acceptable. Many of us wear them all day. And so to move from small shoeboxes, 0.5 kilogram on your head, to true glasses, that's a challenge that no one has cracked, despite decades of research and investment in allied fields. So here's the first publication I ever did in AR and VR. It was back when I was at NVIDIA. I didn't know this full story, but I felt it in my bones that form factor was the problem. And so here's the first AR VR headset I built. It's a near-eye light-filled display. This is my friend Yunta wearing it. He's my colleague who sat in the same cubicle. So about a decade ago, we built this thing. I built this thing with Dave Lubke. And you can see it. It tries to address the form factor thing. The box on top of the head, if I was a better engineer, I could eliminate. At the time, I couldn't. But the real device is a sub-centimeter display that weighs a handful of grams that gives you an immersive or somewhat immersive VR experience. So here you can see the camera moving in. Now, the way it does this is use light-filled technology, which, of course, Professor Hua has pioneered as well. There's trade-offs. There's always trade-offs, as every optical scientist knows, on resolution, MTF, form factor. But this just shows there's something, right? The field had never made a VR headset this thin with this level of image quality, to my knowledge. And it was about changing the game. The real idea here is very simple. Instead of having one eyepiece, you tiled them and have them blend on the retina. And so it's just crossing over from a ZMAX design with a single eyepiece and some surfaces to one that's densely tiled and where your image plane needs some computational optimization. So this is where the idea of computational displays comes in. And it's where I think traditional training leaves us short, that this is not, until recent years, a way we would skin the cat in this problem. And so that was my opening in the field, is since I'm not coming from traditional optical sciences, I came in a little bit with an outsider view, and I didn't know better, right? Like I knew what MTF was, but I didn't really care. I was just like, let's try it. And so I think that spirit continues in my team, is that this idea of looking at problems from an outsider perspective is key. So we returned to this problem over the last few years. And I said, let's really do it for real this time. Instead of having a good prototype, let's get one that's actually usable, that has the same resolution as a modern headset, but is even thinner than what we magicked together a decade ago. And so here's an existing Rift headset. Here's the actual prototype that works that we built. So we did successfully build VR glasses. We moved the driver electronics off the head. And Andrew Mamone, who led this project, found a way to actually preserve the full resolution of the display underneath. And so this is possible. This is not science fiction anymore. This has been demonstrated, right? So form factor of VR can go much beyond what we've seen in the industry. Of course, there are challenges, but it's no longer a question. It's sort of, can we get there in a practical manner? How did we do it? Well, something has to change. Brilliant people came before us. No doubt they had the same ideas. In fact, some of the ideas in this came from the late 70s flight simulator technologies. But what really changed is we got a hold of holographic films, and we developed exposure systems that allowed us to pattern this. And using modern components, we were able to build a very convincing demo. And so I think just sort of embracing a holographic optical element as the only viewing optic, the core viewing optic, was relatively new at the time. And so here is the eyepiece of the system. In this case, it's a single reflective HOE patterned by Andrew on a little optic table. And here's, for those of you who need a ray diagram, here it is. So you got your conventional Fresnel lens, the thing that's inside almost every VR headset up to the last year on the left. In the middle, you see the current, pretty much every headset that's on the market or coming to market has a pancake lens, which does a single fold. what this holocake does is it is fundamentally a pancake lens where the rays fold internally, but at some point, as the device gets thinner, the sag, the thickness of these refractive elements of a pancake become the dominant thickness. It's what keeps you from getting to eyeglasses. So Andrew realized he could compress it down into a single HOE. Of course, that puts requirements on the illumination wavelength properties. The whole system has to change. That's the name of the team. You got to change everything. But we can get this thing down. And so here's the first prototype that Andrew built. This is the entire display subsystem. You put this inside of plastic frames and you have a VR headset. So it's a conventional LCD, only we modified it to have a laser backlight with narrow band illumination to handle the dispersion. And then it passes through an HOE, right? And we exploit selectivity. So it does nothing on the first pass, hits a reflective polarizer like a pancake, comes back, gets your optical power and goes out to the eye. And it's a little less than 9 millimeters thick. So here's what that first prototype looked like when you put a housing around it. And so, yeah, the MTF is not terrible for a research prototype. If you do a little more engineering, you can do that in color. And this is when we found, like, without intentionally trying, we actually addressed another aspect here, which is due to the 3 narrowband laser illumination, we actually have a wide color gamut display. It's the best color gamut I've ever seen in a VR headset to date, including really nice OLED headsets. And so that's also just a sign, like, as an industrial researcher, when you start having a design that solves other problems, not just resolution and form factor, but color gamut, it starts feeling like maybe you're on the right direction. So we spent another year after that first prototype, and we decided to treat this like a startup. So we built a full working headset that plays every single game that Meta has ever shipped. And you can see what it is. I mean, it's not the thinnest this design would allow, but it's fully functional with integrated laser illumination, whole thing. Here it is playing Beat Saber. And so this is the part where if I was an academic researcher, I would not have had the time, the resources, or the motivation. I can't publish this thing, but this is where I feel an industrial research team has to do this, right? You can't stop at just the optical diagram in an optics publication. If you're really going to push the industry to do this, you got to show it, not just to your colleagues at work, but here in an audience at Arizona. So there you have it. So what else did we learn? Well, as a graduate student, I learned to be opportunistic. And so, we had set out on this path to create a thin form factor headset, but then we popped up and we said, okay, HOEs, diffractive optics, seem to be a lever arm that hasn't been fully exploited by others before, to our knowledge. What else could we do with it? And so Changwan Zhang, who's another researcher in my team, decided first he'd find a way to fabricate free-form holographic optical elements. And so you can read about this in our publication, but he and Gong Li, another researcher, developed this comprehensive pipeline to do free-form holographic optical elements. And then we just started applying it to every problem, not just viewing optics, but of course, other things. And so here's one example. Eye tracking, no surprise, is a core challenge. Most displays in VR and AR need an eye tracker to have the best performance. And we'll get into that as time allows. And so how do you create a thin, lightweight eye tracker that can estimate the state of the eye, its rotation, its translation, the position of the entrance pupil, the dilation of the eye, everything very precisely? Well, one way to do that is to have many views of the eye. And so some of the modern VR headsets and AR headsets, you'll see 2 cameras per eye or more. But of course, now you get system complexity. Here, what we showed is with the same holographic treatment on the front of the lens, a very thin film, we could put a different diffractive pattern into it, and a single camera looking back at that film would then get multiple views of your eye. And so we'll talk about how this all comes together at the end. But this is, again, as a researcher, you start to see, hey, not only do we find a thin headset, we found a way to make a thin eye tracker with it that's potentially better than existing eye trackers. So that's what we did on resolution, form factor, and color gamut. Now let me dive into problem 2. So I said there were 2 problems, realism and comfort. Something like holocake would move us, I think, to a new plateau of comfort, right? We'd move from things that are 7 centimeters thick to maybe around 1 centimeter. We'd move from half a kilogram, maybe to hundreds of grams if we're lucky. Great, but I'm not going to use this thing unless there's enough resolution for my task. And so I think a good bar is the idea of retinal resolution, right? That's been so heavily marketed and ingrained. We have enough resolution on our displays in our life to get the equivalent of 20/20 acuity or 1 arc minute per pixel. We don't get that in VR. So the question is, of course, how do you have enough pixels to even achieve that over a wide field of view? But then we get an optical science question is, how do you build a lens whose MTF is good enough to resolve all those pixels? So let's dive into resolution. I'll just give you a quick sense of where the field is at. If you think about it as an eye chart, probably 10 years ago, the first wave of modern VR, headsets were around 2100 visual acuity. So they could depict the second line on a Snellen eye chart. Over the last few years, panels have improved. We've switched to pancake lenses. We're starting to see devices that reach maybe 2040 acuity. And then announced devices, things that are achievable, are getting up to 20/20 acuity. And if you think about pixels per degree, we're in that territory now of around 20 to 30 pixels per degree. We were in the 10-ish or 12-ish. And within the next few years, we'll get into the 40s and beyond. So retinal resolution is coming, but we need to do it without adding more and more surfaces, more and more complexity to get that resolution, to suppress the aberrations, to eliminate pupil swim. We need something very elegant that can reach these resolutions. So how did our team approach this? Well, this will just give you another flavor of how we're tackling research. You saw one version, which is just go towards a destination, think creatively, and make a startup and build HoloCake. I think with resolution, there's a key question, which is how much is enough? Maybe 40 pixels per degree is fine in VR, because you can track the head so precisely and do subpixel rendering and spatiotemporal anti-aliasing and get super res, maybe. Well, the only way to find out is to do it. So on this path, prototyping sort of became our core thing. So once we built HoloCake, we did measure the MTF experimentally just to see where we were at. And so here's what Andrew had. So what we did here is we took the exact same viewing optic, the one we built custom in our lab. We put a chrome on glass target behind it, where we have better than 1 arc minute little eye chart, same thing, test chart that everyone would do across the entire field. So here, even though we're looking at a field that's tens of degrees off center, you can actually resolve with that existing optic, just a single diffractive optic, 1 arc minute. The MTF is not perfect there, but there's another sign that this is a good direction to go, that we didn't have to add more surfaces to actually resolve. We have a thin eyeglasses form factor that if you had a high resolution panel, could resolve 1 arc minute already. But then we get to that question of do we even need 1 arc minute? So there's a whole other side of our research that I'll try to cover today, which is about skipping ahead to the solution, the experiential solution. And so a few years ago, I gave Yang Zhao, who's a graduate of Rochester, the challenge, hey, can we build a retinal resolution headset tomorrow, right? How would you do it? And this is what Yang came back with. So there's only so many panels we could choose from. What's available, at least publicly, is a 3K by 3K LCD panel to us as researchers. This is something that you could source at Arizona. It's not some special thing that only a big company could get. So we were able to easily get a 3K LCD. And with that, you do the math. If you want 1 arc minute over as much of the field as possible, you have to reduce the field of view, or you have to induce extremely high distortion. And so Yang came up with this design, which has about a 55 pixels per degree, so just short of 60 ppd, which is that retinal resolution threshold, over about a 50-degree field of view. So a little more than half of what a normal VR headset would be. But to handle the MTF problem, he did introduce a hybrid lens design. So here, he introduced a dispersive LC diffractive lens to compensate for the refractive doublet. And so this, again, it's our multiple programs feeding together. We developed this expertise making diffractive elements in the HoloCake program. And here we could apply the same element with a much lower power to make, something where the chromatic aberration didn't limit the visual acuity. So this is being presented by Yang at the IODC this year. So very proud of this innovation. If you have questions, let me know and I'll put you in contact with Yang. Here's the device we built. It's not pretty because it's just meant to experience retinal resolution. And if you take a photo through the lens, here's sort of how it lands. So you can see why we wanted this. The Rift, which existed a few years after I started at Oculus, you can see it's just extremely low resolution, 20/90 visual acuity. Quest 2, which is now a little out of date when we made this figure, is about 20/60. And here's Butterscotch, the thing Yang built, which is 55 pixels per degree, which is basically 20/20. And this is real images through the lens. And so for us, this is the first time we got to experience retinal resolution VR. And with that, we could answer a lot of questions. And we'll get into that. But when you worry about all the problems, vergence accommodation, chromatic aberration, form factor, glasses prescription, having a base viewing optic and display that can reach retinal resolution means now we can start doing perceptual studies on all the other requirements. So this is a real unblocker. It's a time machine, if you will, that lets us experience retinal resolution before the panels in the industry allow us. Okay, so that's form factor, resolution, color gamut. If you're playing the game at home, the question is, what do you do next, right? It's not clear, right? As a consumer, I love high dynamic range. As someone who reads a lot of perceptual science literature, I worry about the optical distortions that non-direct view displays have. But when I started at Oculus 9 years ago, there was a lot of worry in the community about vergence accommodation conflict. And so that is actually the first problem. Before I even had a team, it was just me and some really brilliant engineers working together. We decided to tackle about 9 years ago. And the way we were tackling it was to try to find a solution that would be viable within the next decade for a company like Oculus making VR type optics. So if you don't know about this problem, we're getting more nuanced. Everyone can understand resolution. Everyone can understand form factor. Most people could understand color gamut intuitively. Accommodation, I need some slides. So in the 2015, we had this little demo in a prototype Rift, not developed by my team, but developed by the product team, that had a little tiny paper town here. It's like dollhouse style town. And it was very compelling. You could look around and everything's 3D and you can lean in. And my manager, Michael Abrash, said, oh, the best thing is when you lean in like this, you can see like the little characters and the campfires. And it's just so detailed and so incredible. But then I tried it and I'd encourage visitors to try it. And none of us saw what Michael saw. Instead of seeing this crisp, beautiful 3D image up close, we saw this blurry mess. And the reason for that is vergence accommodation conflict. Michael wears bifocals or progressive lenses, and as a result, he no longer accommodates to near objects. But I and other visitors still do at the time, and I still mostly do now. So when you look at something close, your eye tries to accommodate, it throws the virtual screen out of focus, everything's blurry. So you got to solve this so-called vergence accommodation problem. So effectively, it's just playing around with the collimation of the light rays. We need a diverging ray of light to appear as if it came from this close object. We can't do that with a screen at a fixed focus. So in 2017, I had an intern, Nathan Matsuda, who's now on the team. And together, along with other colleagues, we just made a giant table. We're like, okay, this isn't rocket science. There's many, many ways to affect the focus, all the way from just ignoring the problem with fixed focus to doing brute force holography. And we just thought, not where is there an interesting paper we can publish something, because any sort of cell in this table, you could publish something. But what we were looking for is where the lever arm of research could actually bring a solution about without waiting forever. And so when we looked at this table and we debated this table in terms of resolution, eye box, all the things that matter to consumers, that matter for eye health and eye comfort and all those aspects, you could, if you squint, you can see that only one row looks particularly promising, which is varifocal. It's mostly green. Other than to make this thing work, you're going to need eye tracking, which was not common on headsets at the time. And you're going to need some sort of adaptive optic that can globally change the focus. You need some sort of varifocal lens or some telescoping display, and you need to render the blur digitally. So we're back to a computational display. But other than that, we were pretty confident you could hack apart an Oculus Rift and make a varifocal one in short order. And this idea is what gave birth to my specific team. We decided to tackle this, and we needed electrical engineers, mechanical engineers, vision scientists, computer graphics. It was very interdisciplinary. One researcher could not do this, although I tried as best I can on the first one to get as much of it built with a few engineers. The idea is not new. So again, since I'm pitching this lecture to students out there, I want to encourage you to not worry about non-invented here. So long as you're not trying to get tenure somewhere, non-invented here is an artificial barrier to thinking, in my opinion. So varifocal had been proposed. To my knowledge, Shiwa's paper in 1996 was the first real solid proposal of using a varifocal optic or a moving screen to address vergence accommodation in VR. It was proposed, but to my knowledge, no, they never built the headset. They moved some lenses on an optical bench. And for academic work, moving stuff on an optical bench is fine. But I'm trying to actually get this thing into the world. When I started this project, I'm like, not just looking for a paper, I'm looking for a solution, which means the only way to know if it's good is to build it, right? Is eye tracking going to be good enough? How good does the rendered blur need to be, right? What about pupil swim? And what about magnification changes during varifocal? How does it affect stereoscopic perception, right? How much vertical disparity comes in, that induces discomfort? The only way to do this thing is to build it. So that's what we did. So our goal is very simple. Take an existing VR headset that's a panel and a lens, a Fresnel lens at the time, physically move something, either the lens or the screen, to change the virtual image plane, and just follow that with an eye tracker. It's a very simple idea. The first prototype took us a couple months to build, doing exactly that, just modifying a Rift prototype. But to really perfect this, to really make a great system implementation, took 8 years. I've been working on this with a decent sized team, 5 to 10 of us nonstop for 9 years. And we've gone through many, many generations. We've made wide field of view ones. We've made ones with no moving parts. We've tried everything we can think of to make this elegant. It's been a startup running out inside of this team. And so for those of you ever contemplating a startup, this is what it looks like, except for I didn't have to worry about raising Series A and Series B. We just worried about, could we do it or not? Here's what we did. So 2 or 3 years after 2 years after we started working on this, we succeeded in the initial goal, which is modify a Rift without adding too much weight to make it a fully varifocal headset. And the way we did it was just motors moving a screen, very simple. This was good enough that we could run user studies, which I'll talk about in a minute. So I think if you ever contemplate a startup that's based on vergence accommodation, unless you have a user study, it doesn't matter, right? Are you actually making people more comfortable? Do they prefer it? It's a holistic thing. You only know if you try a bunch of people. Here's what we did to do no moving parts. And so at the time, if you did a Google search like I did to try to find some focusing adaptive optic, right? You'd find all the weird ones we use in astronomy, which are not appropriate for this application, in my opinion, far too expensive. You'd find liquid lenses, but they have a very small clear aperture. They have problems with gravity and sag. You see all these problems. And so moving the screen kept being the best way to do this, or move some intermediate lens if you have a multi-element lens. We felt, if we could not move a part, that would be great. But look at cameras, right? They all just translate some element, right? Some voice coil actuated lens. We could not find a large clear aperture, like 5 centimeter clear aperture, variable focus element that could change over, say, 4 diopters. So we had to invent it. So I recruited a postdoc, Afsin Jamali from Kent State, leader in liquid crystal optics, and inspired from some earlier prototypes we did internal to the lab, started by Scott McEldowney, who's obviously well known at Arizona. We discovered this idea of layering liquid crystal pan-Chratnam Berry phase lenses together with switchable half waves, and we made a discrete varifocal system where you get a power of 2. So, right, if you have 5 layers, you get 2 to the 5 focal planes. And so here, when you apply a voltage or not, you can affect the focus between 2 planes with very good MTF and not too much crosstalk. And then digitally, if you can synchronize that, you can have a smooth or quasi-smooth varifocal system. And so this is just a few millimeter thick widget that has a large clear aperture that we can throw into an existing VR headset and get a varifocal device. And so this, for those of you who are more on the component level innovation, that's what it looks. Our system team aspires to work at the system level, but occasionally the device doesn't exist. The widget doesn't exist, so we had to build it. And it used new components, right? Just like the HOEs before, these PBP lenses are not widely used at the time. So I think that's another clue, is if you're working in this field, if you don't have some new material in your system, you're probably not doing anything new because people probably thought of the idea already. That's a lesson I've learned, is everyone's going to think of every idea. So the second there's a new material, try to do something new with it. So this is an example of how the system looked. Hopefully you saw it play back. But to get to this point is what took so many years, right? It was one thing to build a little focusing widget. It was a whole another to put it inside a headset, to manage the haze, the attenuation, to synchronize it with the display, to correct the distortion so smoothly that you don't see popping and jumps and color balance changes as the focal states move, right? This is that long tail that takes years for a good team to do. That's not rewarded. It's like section 5 of your paper. It's one paragraph. This is the difference between industrial research and academia, I've learned, is that long tail is what makes all the difference. But you have to have some motivation besides a publication, because it's just not publication-worthy stuff. All right, so this is what I really was aspired to answer, is that I knew a varifocal headset could be built by a good engineering team. What I didn't know is, did it matter? Lots of companies had worked on accommodation, vergence conflict. Lots of academics had, but no one had ever experimented on it in VR with good eye tracking to answer a simple question. Does it improve comfort? Is it preferred? So that's what we did. So this was inspired by Marty Banks' work at Berkeley. And he did the same thing for 3D TVs and cinemas. He, through the Shibata paper, answered, does vergence accommodation conflict cause discomfort for a 3D TV or a 3D cinema? And he came up with rules of thumb that were well validated. We did something similar, led by Marina Zanoli, who was one of the graduates from that lab. Here's Marina in 2017 doing our user study. So we brought through many, many dozens of people, had them try a varifocal headset with and without variable focus, put them through a battery of holistic tests, not just like Gabor things flashing at different angles, but like play a video game for 10 minutes. Try to fuse a stereogram in a natural environment. Try to do a visual search task. We spent that time in the environment, gathers the statistics, and here's what we found. So wearers experienced less fatigue, nausea, and blurry vision with varifocal. They were able to identify small objects better, had easier time reading text, and their visual environment could be searched more quickly. So just across the board, uniform benefits to varifocal. And I think even though we spent years developing all these prototypes, that was the lasting contribution, is we found it's worth doing. Of course, with the engineering, we found it's possible to do. But I think for a research team, there's one final step, which is a talk like this is still pointless. I'm just telling you, right? I could be bragging, I could be obfuscating the hard things. And so just this year, we did the final step, I feel, of a research team, which is we showed it not to one person, not to 5 reviewers, but to thousands. So Yang took the headset he built that achieved retinal resolution, together with our engineering team, turned it into a varifocal headset with one goal, which was to take it to the world and show it freely. No NDA required, no nothing. Just go to SIGGRAPH, which was held in Los Angeles in early August of this year, and try it. Over 1,000 people did. This coming week, it's being demoed to like 30,000 people, or up to 30,000 people at DC Expo in Japan. So we're taking this on a world tour, and we're trying to share what we learned, right? This has been commented on and reported on for a long time in the press. But what really matters is not what I say about it, but what you think about it. And so, hopefully I can bring this, or if you visit Meta, you can come see this anytime here up in Seattle if it's in our demo room. But this is what the demo looked like. So this is what 8 years of our startup could produce. We have a high resolution environment with small text, trying to emulate cell phones held close, smartwatches held close, tablets, TVs. We already know that we can increase comfort, but now it's just, is it good, right? Like as you look around, do you notice distortion? Is it distracting? Is it frustrating? Those were the questions we wanted to answer. And so I'll really leave it here. I'm not going to tell you whether it was good or bad, because I want you to come see it. But I think in general, the response was positive. And so I now feel like we've pushed the industry. We know it's possible. We know the benefits. And now it's a question of like, well, are the benefits enough, right? And is it possible enough in the sense it doesn't detract from other systems? These are all big questions. But I think from the science side, we've done what we could. So if you're curious about this, you can read about it in our publication, which came out with the eTech presentation. Okay, so I know I don't have infinite time, and I do want to get to Q&A. So normally, I would tell you, we've solved resolution, sort of. Accommodation has a plausible story. Form factor has a plausible new plateau we can reach. Color gamut, we've expanded. What do you want next? And so here, you could debate this. What do any of us want? I think for me, what you would want next is a high dynamic range display. And part of this is just, we're going for that Turing test. And if you've ever seen a true HDR display, like not what you see in an electronics store or what's sitting in your home, but go to Dolby and try a 10,000 nit prototype or 5,000 nit prototype, like the Pulsar display. A true HDR display is extremely compelling. Even if it's not 3D, it almost feels 3D. And so if we're trying to push the unique aspects of the Turing test in wearable displays, the dynamic range is one to tackle. And I think there's a better hope to tackle it because it's a personal device. Every single photon we produce can be funneled onto your retina. You're not trying to spray it across a giant audience on a couch or in a theater. There's a chance that you could create a 10,000 nit display. So I'm not going to dive through this full section because I think you get the gist of it. But we did build such a display. We call it Starburst. Here's what it looks like. So we exhibit this at SIGGRAPH in 2022. So again, like we're trying to set this bar that those of us in the industry who are allowed to publish, we shouldn't just publish, we should be demoing these things publicly to the degree we can so that the whole industry knows what direction to go. So we demonstrated this also to 1,000 people in Vancouver. You're welcome to see this if it happens to be available in our demo room at any given time you're around, just email me. And what we found is we ran another user study. And so that tends to be a trend, much like resolution, much like accommodation. It turns out there's a lot of discussion about VR and AR requirements, but there's relatively little literature on comprehensive user studies. And so there's never been an HDR headset. No one's ever really studied what people prefer. We did that. It was a small study, but we brought, a few dozen people through, showed them HDR scenes rendered on a 20,000 nit headset with different rendering options. We tried to reproduce the luminance one-to-one of an indoor scene on the headset, of an outdoor scene with some sort of tone mapping operator. And what we found, and there's a variety of publications you can find on this now from our team, is not surprisingly, people prefer more brightness. So believe it or not, this is something that you will have a debate in if you work in the industry. Most headsets are around 100 nits. That's a little dimmer than a typical monitor, but you're in this closed environment. And so you'll hear this debate like, well, that's already too bright. If I bring up a browser window in VR, it's blindingly bright. And I only want it at 80 nits. That's true. But a browser window is not a natural scene. If you were to try to depict my office here in virtual reality, what this little chart says is that you'd want something over 300 nits just to sort of feel in the perceptual ballpark of good. And then if you wanted to depict an outdoor scene, you're getting twice that or more. And these are non-experts, right? This is just subjectively, people want a lot more brightness than these headsets produce, which is great news as a researcher because it's hard to make these things bright. Use a waveguide, grossly inefficient. Use a pancake, grossly inefficient, but less so than a waveguide. All these devices want to absorb our photons. Thing is, we're generating a lot of heat on your head. And so if you want to make this thing a lot brighter, you have a real problem. And so high efficiency optics now becomes a challenge. And even if you had that, you need high contrast optics, right? You need to preserve not just the bright things, but the dark things stay dark. And so the contrast requirements that we're seeing in VR and AR designs likely aren't sufficient for a true HDR device of this class. So there's plenty of room for innovation and publications if you're looking for it. All right, so that's HDR. And I probably have enough time to do a few topics if I'm quick. So let me dive into the next one. So those are most of the Turing test things. Now we come to sort of this latest phase of AR and VR, which is mixed reality, right? We're starting to imagine a world where we can have glasses that are highly realistic. But what do I want to depict on them? Well, maybe just the room I'm in would be a good start. Maybe just seeing my face through the glasses, right? Having the equivalent of optical see-through. Maybe that would be a way to make these things just more comfortable, more natural, like normal glasses. How do you do that? Well, right now we put cameras on the outside and there's a host of distortions we need to solve. There's still distortions in the lens that need to be solved, but I think the distortions of pass-through cameras are even greater. So that's the last topic I want to talk about. And this is some of the most recent work from my team. And so let's talk about one particular distortion in electronic see-through, video see-through VR, like the current wave of MR headsets we're seeing. Well, if you take something like Quest Pro, which is, an MR headset from my company, if you put it in a pass-through mode, what you're trying to do is grab images from this yellow camera far away from your face and reproject them perspective-wise as if they were coming from a purple camera that was inside of your eye. Doing that obviously is a major challenge, right? Even if you had a perfect depth map, you're going to have occlusions, and so there's going to be missing data. As I move my hand, there'll be occlusions of regions in the background I cannot see. Maybe I saw them in a previous frame. Maybe I have a really great prior of what all the objects are, but I still have some missing data I need to guess at. So there's different things you can do. In this video, you can see the solution is to not really show those occlusions, but to distort around them. And that works well for objects far away, but not nearby. So this was a problem that's not a display problem. It's a computational imaging problem. How do we design cameras, algorithms, and perceptually make them indistinguishable? How do we get the image we want, even though the cameras can't be where we want? So Lei Xiao on my team, who's a computational imaging researcher, he's the lead of my imaging team. He decided to tackle this over the last few years, and he built the first AI-assisted pass-through system we call neural pass-through. And what's interesting about this, everyone throws out AI, but here, what's different is it has to work in real time, right? So when you see all these wonderful papers on NERF and scene reconstruction and Gaussian splatting, the inference might happen in real time. But building that model, especially for dynamic scenes, generally are not close to meeting the real-time constraint. And so when we say AI, this is real-time AI that's taking live camera images and doing its best to borrow classic computer vision, modern machine learning and AI to create a perspective correct image. And this is what we were able to get. So here the cameras are many centimeters away from where the eyes are. And this is reprojecting that data in real time back to the perspective of your eye. And so you can see there's some flying pixels and some noise, but compared to the video you saw earlier, we can get very accurate perspective on the hands. We can in-paint occlusions in the background. And so this is showing perhaps there's a path that just by pure computation, we can have cameras, sensors that are not where your eyes are, but create perspective correct images. But for my team, there's always a question, how good does it need to be, right? The side that's time machines and perceptual test beds, we wanted that in this program. And so I'm going fast because I have a lot of material, but normally I'd pause and challenge you to think in the audience, how would you cheat, right? We cheated in resolution by getting a high-res panel and lowering the field of view to get to retinal resolution earlier than the industry could. We cheated on varifocal by just moving a screen with motors. How do you cheat in mixed reality? How do you get an image from a camera that's at your pupil of your eye? Do you wear a contact lens with a camera? Probably not. So this is what my team decided to do. It took a few weeks to do, but we created a perspective correct time machine, if you will, where we just took some cameras, put them on stalks, looking back at a mirror. And so I hadn't seen this done before, but this is the sort of thing, again, like it's not courage in academia. You couldn't publish this. But if you don't do this and you just skip right to like NERF algorithms trying to reproject, you're missing something. You don't know what the requirements on the latency, the perspective, the distortion are, but you can find it with something like this, right? Because that mirror is just relaying the camera back to your eye. And so here's what that prototype looked like. Here you can see my colleague, Eric, reaching for coffee. And in the center of the field of view, when it becomes good, that's perfect pass-through. Other than the latency and other things, it's, perspective correct pass-through. And then when it becomes distorted everywhere or in the periphery, you're seeing pass-through of Rift S, which is using that warping algorithm you saw earlier. So to my knowledge, I and my team members are the first to experience perspective correct pass-through. And what we can now do is we can just perturb that camera, right? We can introduce artificial latency in the frames and see what's tolerable. We can put little tuning screws and we can mess the camera up by a few millimeters from your eye. We've published that work. Phil Guan led that if you're interested. But for the first time, we can know what the requirements are for reprojection. But we can't probably ship it, right? This is a photo of me wearing the device. And so you can see Eric's head reflected in mine. I think if you're really clever optical scientist, maybe you could like do something clever here and make it not objectionable. But this is purely a time machine. So where that leaves us is trying to make, sort of like varifocal. We had a time machine to see it, but then we had to figure out over the years how to do it practically. And so Grace Kuo and my team led an effort over the last couple of years to try to build a fully perspective correct camera that is as flat as possible so that you could put it on the front of a headset and have perspective correct pass-through, even though the cameras are not where your eye is located. And so this is repurposing old ideas from light field displays, but in a way that doesn't lose the same degree of resolution they're known for losing. So here's an illustration from Grace, right? Camera on the front of a headset, it looks fine, but compared to a camera at your eye, there's a huge amount of distortion, perspective distortion that needs to be corrected, often by estimating a depth map, filling in holes, all those expensive steps that lead to artifacts. What Grace realized after a lot of iteration was we can use a microlens array and a sensor, and with just the right apertures placed into this, which is the unique part. Most light field systems don't have this aperture array because it eliminates the benefit of a light field camera. With the apertures in the right position, we can actually build a thin headset whose entrance pupil of that effective camera is exactly or very, very close to where your eye should be. So just to show you that entrance pupil, here's a video Grace recorded. You're looking back through and you're seeing the image of that aperture array through the microlens array, and it appears as a single aperture located several centimeters behind the array. So the entrance pupil of this light field camera is roughly where your eye should be in a VR headset. So that's how we created a fully flat, high resolution camera that is perspective correct. No computer vision trickery needed or no sophisticated trickery. So here's how it worked out. Here's my colleague Dusty walking around in our old office. This is a camera looking into the room, and then you put the headset down and you can swipe between them and you can see there's essentially no perspective distortion. Obviously, there's latency, color gamut issues, dynamic range of the camera, but perspective-wise, we can solve that problem. So there you have it. And so then to wrap things up and take some questions, I'll talk about a related problem. So imagine you can actually solve this perspective problem in VR. I can have some magical camera or magical algorithm that allows me to see through the sensors to reality. So I could feel comfortable. I'm sitting in a coffee shop and I can see everything around me. But what will make you uncomfortable, in my opinion, is you can't see through the opaque headset. And that's still the reason I think we believe AR has a better chance. If we start with an optical see-through device, you can see my eyes, I can see you. It's natural. We haven't done any harm. We're just starting with glasses. But optical see-through AR has a lot of challenges. Field of view is limited. The contrast of waveguides and other technologies is usually quite poor. It's not a slam dunk. It's not going to give you necessarily a VR class experience with the technologies we have. And so Nathan on my team, who I mentioned earlier, took this on as a challenge. And we are a team that likes light fields. He solved it by creating the first reverse pass-through light field display on the outside of a headset. So here's a video we did from 2021. This was also an emerging technologies demonstration, but during the pandemic. So we would have shown this publicly, but we couldn't at the time. So again, this is the sort of thing we try to keep in our demo room when visitors are coming. What you can see is that in the left side is a normal VR headset that occludes your face. In the middle is seriously what was published. And I shouldn't laugh. This was seriously considered in the human-computer interaction community. Just stick an LCD panel on the outside of a VR headset and basically paste the video feed from your eyes. And that's what you're seeing in the middle here. And in a photo, that could look okay. And if you had a tracker watching a single external viewer, you might be able to like play with the perspective and make it look sort of okay. But on the right, since we have a light field display, it's a glasses-free 3D display, just shrunk down on the front of a headset. That means within the viewing cone of that display, you can get accurate 3D perspective. And so we can make it feel as if Nathan's virtual face is just coming through. So this is what electronic see-through looks like in reverse. We call it reverse pass-through. It was a small project Nathan dabbled on and off over the years, but we did push this out to the world, and I think there was a positive reception. We are seeing this in the industry now, which is our goal, to motivate the industry to try some wacky things. Here's the actual device. If you're curious about how it works more, we can talk about that after the fact. And then more recently, Nathan started running high quality avatars on the system. And so you can see that playing back. And so I think, this is now showing it's possible. It's just a question of when the industry wants to do it. And they are now doing it. So very gratifying to see the industry sort of moving on the path we were hoping. So there you have it. A bunch of prototyping, a bunch of systems. Hopefully you found it interesting. It's not my goal to brag. I'm very, very proud of the 24 or so people who helped make all this happen. It's a joy to lead a team like this. And I think we're doing well. We've stayed focused on all these problems. How close are we to passing the Turing test? Well, probably not that close, right? This is a grandiose dream of passing the Turing test. And I think through dozens of prototypes, we'll eventually get there. But we're getting closer. Here's a rendering. This is what I'll leave you on, of a device we felt a few years ago that is practical to build now, using holocake, using multi-view eye tracking, using reverse pass-through with hardware components that exist. We believe this headset, which we call Mirror Lake, which is just a rendering here, is actually achievable. And so I think the industry is ready to move to another plateau. Happy to take questions. Thank you so much.
That was a fantastic talk, Doug. Thank you so much.
Thank you.
Yes.
Wonderful talk. Thank you. Nice technologies you have developed. But it seems like you are working through the middleman. The middleman is the eye and the retina. Are there any plans to work directly with the visual cortex so that you can just feed the signal directly to the back of the head and without using any optical element at all?
Yeah, so I think obviously like the idea of direct retinal interfaces is very compelling, right? Science fiction has predicted it. Perhaps one day we will have it. We all have our swim lanes. And I think for me, I'm in my mid-40s now. I feel there's traction here. Like when I started at Oculus, what I was known for was multi-layered displays using like tensor factorization and like quasi-holographic light field displays. And those ideas were something that one or two researchers could build, but were still deemed wildly impractical for the industry, right? Neither of those things have shipped from any company more than a decade later. And so I think when I got to Oculus, right, deciding I was going to become an industrial researcher, or at least give it a serious try in the top company, I had to be realistic. Like, things like light field displays and 3D TVs, like with layered technologies, even those realistically are going to take decades to enter the mainstream. And so for me, with my interests and talents, it's like, I don't want to work on stuff that's 3 years away. I find that, not exciting. Many people can do it. Many people are great at it. It's not my strength. I want to work on stuff that's just beyond the horizon, stuff that seems wacky now, but in 10 years could just be commonplace. So it's sort of what could you build a startup on in many ways is how my research panned out. And maybe it's why I'm in industry and not academia, those sort of things. But when I think about direct neural interfaces, right, as a kid in the 90s, I'd watch shows on the Discovery Channel and you'd see like rudimentary direct neural displays, right? They're doing a surgery and they insert an electrode and they can make a star appear in one part of your visual field. And maybe they can get 20 stars. And this is all very exciting. But realistically, right, I have a good friend, Ram Srinivasan, who used to work in this field, neural prosthetics, scar tissue, all the problems you see with direct neural implants. To my knowledge, they haven't made huge progress. And realistically, they shouldn't. Medical approvals, these things are going to be tested to death. Do I think we'll have such displays in a century? Certainly it's possible. Do I think we'll have them in 10 to 20 years, which is the timeline I'm trying to work on? Absolutely not. Not unless it's critical to your life, right? Like you are blind and now you can see something, but it's not a visual Turing test. So for me as a researcher, I find it fascinating. I'll read every article with every step of progress, but look at what I actually did. When I got to Oculus, I'm like, all right, you got a Fresnel lens and a screen. I bet you could move that screen to change focus. Even that took 9 years to incubate. Still hasn't shipped from any company. I think got to set your sights on what's achievable. And so for me, that remains someone else's career and not mine.
Hey, thank you. Next question.
Hey, Doug, it's Kevin.
Hey, Kevin.
Hey, quick question. Really like, oh, first off, thanks for coming. On the Flamera presentation, are you guys thinking about more of an adaptive system for achieving a larger depth of focus?
Oh, you mean like a varifocal camera, essentially?
Yeah, exactly, to complement the varifocal.
Yeah, I mean, I think that would be the natural progression. So if those of you don't know, Kevin was an intern on our team, and wonderful to see you in the audience. I think one of the startups I saw 2019, I apologize if I got it wrong to the founders. There's a little company called Lemnis Tech. Many of the members are now at Meta. Lemnis Tech actually gave that demo at SIGGRAPH, right? It's not just my little team doing demos. I pay attention when other great teams do demos. They brought a varifocal headset with a varifocal camera. It was pretty compelling. I mean, the varifocal was not perfect, but it was good enough on both sides. On the camera side, I think for me, it's one of those ones where you got to pick your battles, right? I've learned, I love making all these headsets, but even this Flamera headset, which is how we pronounce it on the team, the Flamera headset, we didn't build it in 2 weeks. This took many months of iterating, half a year of finding the components, building the driver electronics, going through prototypes. And so I think we try to get to the knee of the curve. Like, I know what it would be like to have a varifocal Flamera, but to actually build it, right? To build some sort of varifocal microlens array, or to motorize this giant sensor. Certainly it could be done, but it's like you order that up, you crank away at it. Before you know it, 12 to 18 months have passed and you built a demo, but like, did you learn anything? Or could I have just thrown a varifocal camera onto that camsicle prototype and experienced varifocal VR in weeks? So I think that's one of those ones where, like, not going to tell you everything we planned, because I guess you're not supposed to do that. But I think that one would be a lot of work for not a lot of learning. So we try to avoid that. Being a small team, we can't do everything. But varifocal cameras paired with varifocal, obvious, right? If you've solved the display side, now you got to solve the capture side. I don't think varifocal cameras is nearly as hard, because I can buy those. Can't buy a varifocal display.
Thanks. I have more questions, but I should probably save for everybody else.
Questions?
Any from the online? Don't know.
Hello. When you mentioned that you kind of are reaching a point where you have a limited range of accommodation, I read somewhere that people's accommodation, when it becomes limited, doesn't just plateau. It kind of doesn't reach, it kind of under accommodates for every distance, like to a point. Have you found that there's any issues with people with limited range of accommodation when you look into that?
Yeah, so those of you sitting there with your cell phones, you can find the curve he's talking about if you just type Duane accommodation, D-U-A-N-E, super old chart, and you'll just see that curve, which is sort of depressing, where it shows how many diopters you can accommodate versus age. And you go to your mid-40s like me, and you're like, gonna need bifocals in a few years. So, we found, like, for our demonstrators, 3 to 5 diopters of accommodation was quite compelling for the majority of people. But, think about the engineers and scientists that are in the lab and their typical demographics, blah, blah, blah. Again, sort of like my answer to Kevin, you got to pick your battles. And so there had never been a study on varifocal headsets because they didn't exist. We did a broad study, but we did, in what I just reported, we were careful, like, for pre-presbyopes, as you're describing, like individuals in their 40s and 50s who still have a diopter or two of accommodation, but are going to that plateau point. Their accommodation dynamics, there's a real question, like, what's going on there? And then, of course, once you've reached whatever your plateau, there's a question there. So here's the part that's fun. We now built a varifocal headset. We're demoing it publicly. Can't promise anything, but one of the things is I would love the Marty Banks of the world to have this, right? And I'm very happy to talk to the lawyers and do whatever. I think this is unique. You know, you can't go to a startup and buy a varifocal headset, but we got some. And so I guess the answer would be, you know, my small little team, we got one vision scientist on staff, Phil Guan, can't tackle every problem. So this is an area where if anyone's watching the recording who's a vision scientist and wants to study how presbyopes respond to a really nice varifocal display, you have my ear, and you might get a couple of my headsets to try it with if we're lucky.
Any other questions? Yes. Let's see, do one more.
Where do you stand relative to the Microsoft's HoloLens?
Yeah, I mean, I wouldn't call out Microsoft specifically because, you know, there are a variety of companies that have some sort of similar waveguide display system. Obviously, theirs is, you know, market leading with the complexity and the software system. I think, you know, that comes back to, let me bring up my little chart from the beginning, you know, AR versus VR, right? So it's a question I asked myself. Like when I joined the company, it was going to be a small research lab, really small. And it was just a VR company. But I knew, I was like, yeah, we're going to work on AR pretty soon. And we'll work on light field TVs and everything else I love. And I was mostly right. But the thing is, like, sort of my answer earlier about, hey, can we make contact lens displays or retinal implants? Yeah, we could do those things, but on what time scale? And so, you know, for me, it's not that my team only works on VR. This presentation is VR heavy. We are working on AR as well. But generally, for a systems team, AR is a much steeper slope than VR, right? You could see with just a handful of people. I mean, my team was just like 4 or 5 people for many years. With a very small team, we could get to that Mirror Lake concept. We could build something that's, you know, goggles form factor that's not science fiction with a real parts list that solves a comet. You know, all these things could be done in VR. In AR, not much has changed over the last 10 years I've been working in the field. We knew about waveguides long before HoloLens, right? All the way back to the work at Philips and elsewhere. Waveguides are waveguides. You know, you got geometric ones, you got SRGs, you got all these things. But generally, their performance has not dramatically changed, in my opinion. You know, the basics of it. The problems still remain, you know, uniformity challenges, form factor, field of view challenges. But the constraint hasn't changed. You know, if you're chasing eyeglasses, you got to pack everything in there. And so for me, I've been sitting inside of a company, looking outside, you know, what do I see when I go to a trade show? The progress in AR has been pretty slow, in my opinion, you know, at the fundamental display component level, right? The fields of view are not dramatically different. The image quality is not dramatically better. And part of that is the technology hasn't really changed, you know, making SRGs, making these things. We could do it before, we can do it better now. This is just my personal opinion, watching the industry and just seeing what we see at trade shows. The other thing is it's contingent just as much on VR and display technology, right? You look at VR, it happened in the first place because of the investments made in cell phones. Then a new wave of investment came and gave us VR-specific LCDs and OLEDs and micro OLEDs. And we're starting to plateau on what those things could achieve from off-the-shelf parts. But in AR, right, you got the same old LCOS projectors we had before HoloLens, the same ones we have now. And the challenge of like standing up a new display technology, right? Yeah. My friend Mary Lou Jepson, you know, she said to me once, you know, I hope this is an accurate quote because you shouldn't follow me, listen to what she said, but she's like, Doug, it's 20 years. She used to sit next to me at the lab. It's like 20 years from someone pitching a display technology to it happening. A good example is DMD technology from TI. Brilliantly innovative. One of the most surprising technologies to me that exists in this space. You know, it's just so complex, it shouldn't exist. Took about 20 years, you know, to go through research. And so I think in AR, you know, if you're constrained as you got to pack this thing into glasses, you got to get a wide field of view, it's got to be lightweight. There's just so many constraints compared to VR, which is starting with a pretty big enclosure, and a small research team could crank that thing down to goggles form factor And we even showed a glasses form factor thing. So again, I don't want to say I'm fully opportunistic and I'm not interested in AR, but the low-hanging fruit is most definitely in the MR and VR side. And I think we have not plateaued as an industry. We can take this thing to those glasses I showed, I believe. In AR, I think that's where certainly my team's working. We have a lot of publications on holography that I didn't cover today. There's opportunity there, but you need to be more patient. And you're not going to see a little team just pop up, probably, with some miraculous step forward. You know, smart people have thought about it. The materials aren't necessarily evolving. So I think for you sitting in the audience, you're asking the right question. You know, would I work on VR or AR as a graduate student? AR. Because the gradient is so steep in VR right now, by the time you're a professor or working in industry, perhaps it reached the plateau and it's like AR now, where you're waiting 20 years for a new display. So the pendulum will swing. As VR gets to glasses, everything's glasses. AR is just as hard as VR. Now we got to work harder to take the next step. So I guess VR today, AR tomorrow for me as a researcher.
Okay, any other question from the audience?
Well, just would you share his email address?
Oh, Doug, he's asking you to share your email address.
Very easy. It's first name, period, last name at meta.com or Oculus, or FB, whatever you choose, but douglas.landman@meta.com.
Yeah, Doug, let me ask you a question while others are waiting.
Yeah.
So, this is something that has been puzzling me all the time, and you have been running your research direction almost in similar fashion as I run in my small research group, except you have a humongous budget, right? And so you got
I don't know if I'd agree with the humongous budget, but that's okay. I have a budget.
Yeah, so you build different prototypes, explore different architecture, trying to solve different problems, and my group does the same. And the thing that puzzled me all the time, I don't know how to address this issue, is the different solutions you showed today are trying to address different problems and based on different architecture. But those problems are critical common to VR and AR and the system. How do you see those solutions converge?
Oh, thank you. So it's like I planted the question, which I didn't. This is a perfect question because I skipped over it because I wanted to get to Q&A. Let me just go back for a second. I just played this video, but that is the question, right? Like a couple of years ago, I was sitting around and all these threads were moving ahead, and I sort of felt like, hey, you know, I'm getting to that mid-career stage, and I named my team Display Systems Research. So where's the system, right? And so I have this wall that, you know, probably the thing professionally I'm most proud of is this wall that my brilliant researchers made. And it's just dozens of different threads. Can they come together at all? And so I'll tell you a story, and it's just a story. We haven't built it. But a couple of years ago, I was like, you know, I need to answer that question to myself. Like, are these things mutually incompatible? In which case we haven't really made real progress, or are they leading to something? And, you know, to skip ahead, this thing I did tease, which we call Mirror Lake, it's a concept, but it does have a parts list. Like, it's a real thing that we could build with significant time spent to make it. Here's what that thing is. So again, I am very grateful to Meta that you usually don't get a detailed exploded view diagram of a prototype that took a decade to conceive of, but here it is. Thank you so much for letting me share it. This Mirror Lake concept is one answer. You know, if this was my qualifying exam and you asked that question, here's the answer on how it all comes together. So what's the truth? The truth is we are researchers that are opportunistic, right? We are not faultless. We can't see how all the pieces come together. And so after 10 years of mucking around in this space, we looked around and we just said, how do we put it all together? Here's one answer. So we want it to come together into something that's thinner, lighter, more comfortable for the most people possible. And so I look at what my life is, and sadly, it's a lot less video games than I was young. And so this is first a productivity type concept. So you notice there's no facial interface. The sides of the head are exposed. Air can move freely across your face, and you can see naturally on the outside. You don't feel confined. This is just my team's opinion. This is not some big meta thing. It's just my team. thinking about what we want. So that was the first constraint. So that means you can't pack a lot of electronics and other things in the side region. Also, the weight has to stay very low, which means you may want to tether and put the compute and battery off board. That was the first step. What form factor do we want? We want something that we could actually wear for many hours a day, to be in telepresence calls, to be in meetings, to get 3D visualization data. Okay, now we want that thing to be acceptable to those around us, which means we want the reverse pass-through. We don't have optical see-through. Waveguides are not perfect yet. We want the wide field of views, which means we're making a blocked light VR headset as thin as possible that has the reverse pass-through system. And so here's what we did. Step one is always the lens. And so we learned with HoloCake. So far, I haven't seen a device that thin that can reach 1 arc minute resolution and weighs almost nothing. So it just has a bare panel, laser backlight, and then it goes through our holographic lens, and that gives you the thinnest optical stack that can reach retinal resolution. So there you have that. So then the next step is, how do you get accommodation, which you saw whiz by there. And so the way to get that is this electronic varifocal module I mentioned. So we stack up those PBPs, the switchable half waves, and in a few millimeters, we can tack that thing on the front, and now you can have arbitrarily high numbers of planes of focus, 32, 64 planes of focus. And perceptually, we've shown that that can be very compelling. So now you've solved at least 3 to 4 diopters of varifocal in a compact form factor. Your next challenge, prescription. This thing is so thin and light, you don't want to wear glasses under it, and you don't even want to clip prescription lenses onto it. What I think is, you already have a hologram, put that prescription into the hologram. So this would be obviously a manufacturing challenge, but by baking the prescription correction, you can have sphere, astigmatism, cylinder, all corrected for the individual. And in my opinion, these are personal devices anyways. I don't share my cell phone with anyone. Why do I share my glasses in the future? And so that gives us prescription without any holography, without any magic tricks, just a boring old hologram doing our prescription. So that's the viewing optic. So in like a centimeter scale, with a fraction of the weight we currently have in pancakes, you could have prescription, accommodation, high resolution, high color gamut. There's the display system. So where do you go from there? Well, the next step is you need an eye tracking system. And so I also showed that earlier. We found that the same HOE that can do the viewing eyepiece in a thin system, that can do the prescription correction in a thin system, you can also bake an HOE to give you multi-view eye tracking. So just 2 cameras, 1 on each side looking back in the infrared band, can get multiple views of the eye and give very accurate tracking to drive a varifocal system and to make a very high quality distortion-free display. So again, almost no weight added other than 2 cameras to track the eyes, which is less than state-of-the-art commercial systems. Then we have to give you back the great pass-through. And so using the neural pass-through algorithms with off-board compute, like Lei was showing, a couple cameras on the front can reproject. Don't use that light field thing I talked about. Just use some cameras and some good algorithms is, I think, the way to go. And then finally, the real missing piece is, if I'm going to wear this for hours a day around my coworkers, with my family at the kitchen table in the morning, you have to be able to see my face. You have to feel comfortable in the environment. And so you need the reverse pass-through display. And so far, the only way we've seen to do it in the industry is a light field display on the outside. And so, yeah, I challenged Nathan Matsuda and some brilliant mechanical engineers on my team, electrical engineers, to actually go and develop a parts list. So there is a parts list for this thing, like real switchable half waves, real display panels we can buy, real micro lenses that can be diamond turned. This thing's a real concept. It's not just like, wouldn't it be great one day if we could do this? And so this is what we think you could get. You know, it's not, if you look from the side, it's not completely thin, but it's open. So you can see Nathan's face if you're sitting next to him at your desk. His face is comfortable. We designed a facial interface that has contact not everywhere in your face, so air can flow freely. It's less confining. It's designed for productivity. And then that's an actual simulation in Blender of tracing the rays, including their aberrations through the micro lens, including the pixel structure. This is what we think you could do with the reverse pass-through system. So that's my answer, is this stuff does all come together. It wasn't some giant master plan that happened to, that was all tailored to come together. I'm not that good, but I guess when you have a bunch of brilliant scientists and you turn them loose, they're like me. They're not looking for solutions in 40 years. They're following the gradient of all these subfields, and all those gradients went through holographic optics, and that allowed us to build something that's cohesive. So that's the long-winded answer.
Thank you so much. Any question from the audience? No? Oh, one more.
Hi, Doug. Thanks for the very lovely talk. This is fascinating work. I'm curious. So you obviously take the perspective for the visual Turing test of trying to get the technology to match up with what the human visual, acuity is. Looking in sort of the other direction, is there any work going forward to take these sorts of systems and then try to develop or to add in features that then enhance the human visual system? So now instead of just trying to match, now we try to add in other spectral components or other levels of resolution, telescoping, that sort of thing.
Yeah, so I thought you were going to go the other way, and this I get more often, which is like, do I really need to pass the Turing test? And then I would have said, yeah, probably not. Much like a PhD thesis, you sort of build that. This is my like intro chapter, right? I've done all this work, and I've now I've after the fact made something that makes it seem like it all came together. The Turing test is something we use to motivate our team because we know realistically passing that is a long, long way off. So first, I'm going the other way from what you said, which is not even superhuman. There's a side of this I didn't present in this talk, which is just, can we make something of high utility to individuals, right? Which is a whole separate cross-section of what my team did. And for that, do I need the Turing test to be more productive at work, to have great telepresence, to edit data in 3D? No, probably not. So I think don't over-index on my Turing test thing. It's just like a way, it's the elevator pitch, but everything's always more nuanced. Now, the other direction is certainly fascinating. And so I think we already can do some things that are superhuman, if you will. Here's the easiest one that comes for free. You already have it if you own a VR headset. I'm in my mid-40s. As I get older, my accommodation will go to that plateau. And as I walk around in reality, I'll need bifocals or progressive lenses or some autofocus headset, pair of glasses. But in virtual reality, right? My boss put on that VR headset from a decade ago, and he's like, this is sharper and clearer than I've seen in a long time. So that's an example, right? Where it's not why we have fixed focus, but imagine if we could take the world and collapse it all down onto a stereoscopically correct plane. That's exactly what individuals with presbyopia would want. So there's the first example of, in VR, imagine you're walking around with Kevin's varifocal cameras, but a fixed focus headset. Then that would actually allow individuals who are older with presbyopia to see more clearly. If they're working in the garage, they could lean in as close as they want and see things clearly without their glasses. And so my friend Gordon Wettstein had a startup, Zen Labs, that was potentially commercializing some of those ideas using liquid lenses and other things. So that's one superhuman direction, but not so super. It's just human again. But then, like you said, like, it's very easy to imagine what superhuman looks like. To me, superhuman's interesting, but I think before we get to superhuman, assistive is more interesting to me. So for years, I've gone to conferences and I'd see bad AR glasses used for wonderful assistance, which is like run an edge detector on your camera and highlight high contrast edges. And so for individuals with low vision, they can see the curb next to the crosswalk. It's not Turing test in any way. It's just a bunch of glowing white lines overlaid on their world. But if you do it well, it could transform their life, right? If you have a detached retina and you can barely see, like, maybe this will help a little bit. So I think assistive, before we try to make everyone better, we try to bring everyone to parity as much as possible without neural implants. I'd love that. I find it fascinating. And I think that's where AR shines. MR does have a limit, like I'm talking about a headset here that you can use in an office or with your family. If I'm walking around the world, I do want optical see-through personally. So and then we get to what you said, which is superhuman. And there, sky's the limit, right? I mean, hyperspectral cameras, you can see other color bands, right? You could see heat signatures through walls. I mean, all these things are possible. The question is, like, what's interesting to the most people? And I don't know how to answer that question. So I think increasingly the way I answer these questions is what's interesting to me. Like, say I can order up any magic thing from my wonderful team. Do I need, infrared? Do I need to see in the infrared band for some reason in my life? I don't think so. It would be fun to like play hide and seek with my kids, but I don't need it personally. Do I need telescoping optics so I can get hyper magnification? Maybe, but I can also just put a microscope on my bench in my garage. So this part, I don't know. It's not an angle I've worked on. The Turing test or the less than Turing test is where I'm putting my energy. The hyperhuman capability thing I think is interesting. And to that, I look to academia, to startups, to spark my imagination. It's not the thing I spend most days on. It's like, can I get most people to have a device that makes their life as good as it should be and as productive as it could be before it's like, and now let's have capabilities beyond what we normally have. So I think it's fascinating, but I think AR and VR has to succeed without that. If it doesn't, then, it's just sort of disappointing. Like the only way AR and VR was interesting is to go beyond reality. I think it's enough to just get to reality on a display. No one's ever done it. So I'm answering a lot of these questions like, no, it's not a bad idea. It's just, it's not where I'm putting my energy as a researcher.
Hey, any more? If not, let's thank Doug again for that wonderful talk and the Q&A.
Yes, thank you so much. And again, so honored to talk to the group here. So if you're a professor, student looking for internships or looking for collaborators or looking to borrow a headset, come find me. Thanks for paying attention. Thanks for the invite.
I'll email you to borrow your varifocal.
Yeah, please do.